Okay, continuing our analysis of the trace determinant plane, we now need to look at this region below the parabola where we know we have real eigenvalues. And just to remind you, we used the quadratic formula to find that this was our formula for that. Okay. Now, what I'm going to do first is I'm going to look at the region where t is positive. Okay. Now, I am not assuming here that the d-axis gets to be drawn in pink because it's a distinction. It distinguishes between different types of behavior. I'm not assuming that. I'm just saying strategically it's going to be easier for me to deal with one half of this picture first and then the other half. If it turns out that I get different behavior on either side of the d-axis, I will draw the d-axis in pink because that's the color reserved for boundaries between different types of behavior. Okay. All right. So if I'm looking at t being bigger than 0, okay, then if I look at lambda 1 being t over 2 plus root t squared minus 4d over 2, that's got to be positive because this is positive and this is always going to be positive. So I'm always going to have, if t is positive, one positive eigenvalue for sure. What we need to check then is what's the sign of the other eigenvalue, t over 2 minus, whoops, that was supposed to be t squared, minus root t squared minus 4d over 2. And that's going to be determined by whether this thing, root t squared minus 4d, is bigger than or smaller than t. Okay. Notice, if d is 0, this just becomes the square root of t squared, which is the absolute value of t, which since t is positive, that's going to give me 0. So, if I have d equals 0, then lambda 2 will just be 0, because this will reduce to t over 2 minus t over 2, and I'll get 0. Okay. If d is bigger than 0, if it's positive, now I'm subtracting something positive from t squared. So, t squared minus something positive is smaller than t squared. The square root will then be smaller than the absolute value of t, which in this case is just t, since t is positive. And so I'm going to have a positive number minus a smaller positive number. It will still be positive. If d is less than 0, then minus 4d is actually making t squared bigger. So then t squared minus 4d is bigger than t squared. Its square root is bigger than the absolute value of t, which is t. And so I've got a positive number minus a bigger positive number. I'm going to get that lambda 2 is negative. So it turns out that at least when t is positive, we haven't looked at what happens if t is negative, or, well, I guess we have looked at what happens if t is 0 at this particular point. But at least if t is positive, I know that when d is equal to 0, that's going to be in pink. That's a boundary between different types of behaviors. So I'm going to just draw one point up here. We'll call that G, then we'll have H, and I'll call that I. That wasn't the number E, that's not the imaginary number I. Okay, so let's see if we can't now look at the different types of phase portraits we could get at these locations. So let's see, let me keep this information up. But erase the rest. So G, that was when D was positive. So we knew, remember that lambda 1 was a positive eigenvalue. Now we've got another positive eigenvalue. So at G, I would have 2 positive eigenvalues. So I would have 2 straight line solutions that were distinct. And then I know that my solutions would basically start out tangent to 1, and end up roughly parallel to the other. And so I'd have something that looked something like so. In that case, the equilibrium solution at the origin would be a source. Okay, so that was G. We've dealt with that case. Let's look at H, which is when D is 0. Okay, so then our second eigenvalue is 0. So I'm going to have a line of equilibrium solutions, and not just the origin. And then lambda 1, remember, was still positive. So all of the other solutions are going to move away from an equilibrium solution, not necessarily away from the origin, but in a direction, a straight line that's parallel to the eigenvector for our positive eigenvalue. Okay. In that case, when the origin is not the unique equilibrium solution, we don't bother to classify it. Okay, so we've dealt with that case. Okay. So now I need more space. Oh my goodness, this is so exciting. At point I, we've got that lambda 2 is negative. So we said lambda 1 was positive. So we've got our equilibrium solution. We've got one set of straight line solutions corresponding to a positive eigenvalue. And now we've got another corresponding to a negative. That's going to give me my beautiful and lovely saddle. Okay, fabulous. So that's what we see if T is positive. Let's take a look now at what happens if T is negative. And then we'll also have to take a look at if T is 0, although in that case, we're only going to get real eigenvalues if D is also negative, because once we're up here, we're in the complex zone. Okay. All right. So again, my lambda values are T over 2 plus or minus the square root of T squared minus 4D over 2. And now if we're looking at T being negative, if I take a look at, I'm going to call lambda 1 T over 2 minus root T squared minus 4D over 2, because that's the one whose sign I'm absolutely sure of. This is negative if T is negative. This is a positive that I'm subtracting, so a negative minus a positive, that's going to be negative. So I know for sure that I'm going to have one negative eigenvalue if I'm somewhere over here. And what I want to look at is what lambda 2 is, where lambda 2 would be T over 2 plus root T squared minus 4D over 2. Now, I know that this is a negative number and this is a positive number, so the resulting sign is going to depend on which piece is bigger. Okay. Now, if D is equal to 0, this is just the square root of T squared, which would be the absolute value of T. In this case, because T is negative, that would be the opposite of T. And so these two pieces would add to give me 0. So if D is equal to 0, I'm going to get that lambda 2 is equal to 0. Okay. If D is bigger than 0, let's see, if D is positive, then T squared minus a positive, this is T squared minus a positive number, so it's going to be smaller than T squared. So the square root will be smaller than the absolute value of T. So this positive part is smaller than this negative part. The negative part wins, and lambda 2 is going to be negative. If D is less than 0, now subtracting 4D actually makes this bigger. So what's under the square root is bigger than T squared, the square root is bigger than the absolute value of t. So now the positive part is bigger than the negative part, and so we're going to have that lambda 2 is positive. So it does turn out that the t-axis here does get to be drawn in pink. This is so exciting. Okay, so the t-axis on both sides is a boundary between different types of behavior. Okay. All right, so let's see, so I'm going to put a point here, J, K, and L. All right, and let's see if we can draw a representative phase portrait for each one of those. Okay. I think what I'm going to do, just because this video's been running for a bit, I'm going to stop the video here, keep up this information, and come back in the next video with these. And then I also want to take a look at what happens if D is 0 and T is negative, because that's the one thing we haven't looked at. We broke up this region into T being positive and T being negative, so I do need to take a look at what T is 0. So we'll do that together with getting the phase portraits for these points in the next video.